So as a part of the ongoing amplifier stuff that I'm working on, I wanted to have some temperature ESP32 controlled temperature sensors. And so what I thought I'd do is play around with a few different devices and sort of document the results. So in this video, I'm going to be sort of going through the devices that I've chosen, which are a MAX31865 RTD to digital, a TMP36 temperature sensor. I thought I'd show how we hooked them up to the ESP32. For the temp36, it uses an ADS1115 analog to digital converter. For the MAX31865, it's a SPI interface. Thought I'd go through some challenges and finally do a demo. Okay, so let's talk about the TMP36. So the TMP, and I'll include, as usual, data sheets to all these devices down below. But here's the TMP36. It's in a TO92 package. It's a low voltage temperature sensor. And the pin order of these, how they basically work, is you supply it with voltage. It could be either 3.3 or 5 volts. You give it a ground, and then on the middle pin, you get an output voltage, which is proportional to the temperature. And there's a formula which I'll go through for that. Now note, these devices, and this device I got off Amazon, have a different pinout to the ones on Adafruit. So it goes supply voltage, output voltage, and ground. The Adafruit ones, for some reason, have a different pinout, even though they're called TMP36 over on Adafruit. So basically, to hook up these devices, what I'll be using is the ADS1115 analog to digital board that I've used elsewhere. I could use the ADC on the ESP32, but I thought I'd use the ADS1115 board. The advantage of the ADS1115 board is you can hook up to 4 independent devices on there, and because it uses an I2C interface, you're only using a pair of pins on the microprocessor. Let's move on to the next device, the MAX31865. Okay, so the second device I'll be using is the device you can see here. It's a MAX31865 resistance temperature detector to digital converter. And I'll be using that in combination with a PT100 temperature sensor, temperature sensor probe, which I'll show in a moment. So the MAX31865 here takes either a 2, 3, or 4 wire sensor interface, and it exposes an SPI interface to the ESP32. So the 3 and the 4 wire temperature probes allow the temperature sensor to compensate for the resistance in the wires to the probe, and so thus it provides a greater degree of accuracy on the temperature computation. Just going through the interfaces quickly, at the top here we have the connections for the probe itself, 2, 3, or 4 wire probe. At the bottom, we have the SPI interface. So you can see from left to right, so you supply voltage and ground, and this takes 3.3 or 5 volts. There's actually an onboard voltage regulator here that allows, that powers the IC, and it actually exposes that 3.3 out here. And then here we have the standard SPI interfaces. So you've got the clock, you've got the SDO, which is the same as the MISO. You've got SDI, which is same as MOSI. You've got the chip select, also sometimes referred to as SS in some literature. And then finally, you've got an output pin here, RDY. And what you can do is, as conversions happen in here, it raises this pin high. So you can have an interrupt in your ESP32 that listens to that and acts accordingly. And finally, on the device, you've got these jumpers right here, here, and here, and you have to bridge them appropriately depending on whether you're using a 2, a 3, or a 4 wire device. So for a 3 wire device, which is what I'll be using, you have to bridge this one here. You leave this one alone here. You cut this bridge between the 2 and the 4 pin interface, and you bridge this pad to this pad. So that's the setup with the 3-wire interface. Let's move on and have a look at the probe now. So you can see I've got the probe, the 3-wire probe connected to the MAX board here. So this is this is the actual probe itself. There's a piece of platinum wire in here which responds to temperature by changing resistance. And then you can see the connections here for the 3-wire probe in that the board's actually upside down from the orientation I had before. But the two leftmost connections go with the common, the two red wires, and then this connection is for the blue wire. And then this pin and this pin are actually shorted together depending on the bridge selections that you've got there. So anyway, that's the probe. This probe tip and the cable's actually waterproof, which is one of the advantages. So you can dunk it in water, and we'll do that later on. So let's move on to now the hookup in the ESP32. Okay, so here's the setup I'll be using here. Let me just walk through the connections. So we have the two devices on the left-hand side here. At the top here we have the TMP36, so left pin is voltage source, 3.3 volts. The output comes from the middle pin, and then ground is on the left-hand side. That gets sent to A1 of the ADS 1115, and then the connection to the ESP32 is through SCL and SDA, which go through to pins 27 and 26 respectively. So moving down to the MAX31865, you can see that this is the actual probe that I showed, and then it has a pair of red wires which go into F plus and RTD plus, and then the single blue wire goes into RTD minus. Then connecting the MAX31865 to the ESP32, you can see we have chip select goes through to IO14, MOSI goes to 32, MISO to 35, and then finally clock to pin 19. Okay, so let's just quickly walk through the hookup on the breadboard here. So here's the basically the SPI lines coming from the MAX, and they go into the relevant pins on the ESP32. Here's the TMP36 right here, and I've got that coming. It's powered from this rail right here, which is running at 3.3 volts, and then this orange wire is snaking off to A1 on the ADS 115 board, and then here's the the I2C lines here going into the ESP32. So let's anyway just have a quick look at the temperature measurements themselves, and then we'll do a bit of diving into the code. Okay, so let's see both of these in action. Let me fire off the... you can see I'm reporting the temperature in Celsius for the TMP36 on the left and the MAX on the right there. So let me put my hand around the MAX, and you should see that temperature start to go up, and indeed you are there. Up to 17 degrees, 18, and so on and so forth. So let me do the same thing with the TMP36. You should see that temperature start to rise, and you can see that going up to 17. And then finally, for giggles, let me just stick the probe into some hot water. It was boiling a few moments ago, but it's been cooling in the garage for a bit there. So we're up 76, 77. Looks like it's cooled significantly since it was boiling. So there we go, up to 80 degrees. So that's the MAX31865 probe in there. So that's a demonstration of the functionality. Let's move on to the next step. Okay, so as you can see, I've got my scope probes hooked up to the MAX31865, and let's just move over to the oscilloscope itself, and we'll zoom in that. And so just going from top to bottom, so the yellow trace is the chip select, so that gets pulled low when the master wants to do something with the slave. This trace, the sort of purple trace, is the clock. The blue trace is master in, so master out, slave in. And then there's somewhat messy trace down the bottom is the response from the MAX31865 itself, or the master in, slave out. So let's move into drill into one of the interactions. And again, just to remind that, so the top is chip select, clock, master out, slave in, master in, slave out. And so a typical interaction gets started with the chip select getting pulled low. Once the chip select gets pulled low, then the master starts to issue the clock, and then the clock dictates what transactions are actually happening. So you can see here, the clock starts up here, and this happens to be here to be basically 0, 1. So we go, so this is bit 8, 7, 6, 5, 4, 3, 2, 1, 0. And then this is bit 0. So that basically is writing a 1 to the SPI bus. And you can see that down here. Actually, I've got SPI decode going on here. So a 1 is written here. And then the device itself responds. So the green trace is the device responding. And in this case, a 1 request, register 1 for the MAX31865, is give me the 16 bits of temperature information. So you can see here's the response here, the green trace, and it is 3E AC. And I just checked, and that does indeed match what I got over on the laptop. What were some of the problems here? Well, the first problem that I encountered was basically that the MAX31865 has to detect what mode the SPI is being conducted in. And I'll include a link to the different SPI modes, but a part of that mode is whether we have a positive clock that goes down on clock pulses, or a 0 clock which goes up. So what the MAX31865 does is when the chip select first gets pulled to 0 on an initialization of the board, it attempts to detect clock polarity. The problem is that the clock and the chip select using the standard ESP32 libraries were getting pulled down together at exactly the same time. So there is supposed to be a gap between the first chip select and the first clock pulse. That just simply wasn't happening with the ESP32 libraries. Now, I've had no problems with this, but just the way the Max board is detecting clock polarity just wasn't working. So what I've had to do, and you'll see this in the code, is actually manually do the chip select myself surrounding the SPI transactions. And I'll show that in the code when we get over there. The second problem that I encountered, and this was a bit more problematic, is that if we just drill into the to the response here. So here's that it asks for the temperature, and then it gets this 3E AC response from the Max. What was happening is it would get the first byte, but not the second byte. And I was using ESP-IDF version 4.2.1. There's obviously a bug in that of some description. I had to upgrade to, I tried both 4.3.2 and 4.4, which is in a sort of a beta version. Both of those worked, but 4.2.1 did not work. Okay, so I don't usually do code walkthroughs, but I thought this was pretty interesting. So let's start with the chip select. So the chip select, if you have a look here, these two lines of code here, there is automatic control of the chip select in the SPI library in the ESP32 IDF, and you enable that by just passing it the GPIO pin of whatever it is that you want to use for chip select. Now, this was the part that wasn't working. So I basically you basically disable that by passing -1 in there. And then if we move to the library itself, you can see here I'm manually pulling the chip select pin low just before the transaction, and then pulling it high immediately after the transaction. Okay, so just while we're here, this is the piece of code which reads the double bytes of temperature information. And what was happening in the 4.2 version is this would all succeed, no problems, but the second byte would always be 0. So in this case, I had to upgrade to 4.3.2. So 4.2.1 is pretty old now anyway, so it was a good thing to upgrade. 4.4 also works in this case. So let's just quickly walk through the how the temperature is actually derived with both of these devices. And so this is the piece of code for the TMP36 right here, and it's pretty straightforward. Basically, the temperature is it's 750 millivolts at 25 degrees Celsius, and then above or below that for each degree C, it goes up or down 10 millivolts. So that's the formula there. 750 millivolts at 25 degrees C, and then 0.01 of a volt above and below that is 10 degrees C. So the MAX31865 unfortunately is a little bit more complicated. So here's the formula here, and you'll notice basically this is the resistance using the temperature. So it doesn't give it as temperature equals some formula of resistance. It gives it the other way around, and it's this Callender-Van Dusen equation. So you can see it's a quartic formula here. So it's not easy to actually derive the temperature as a function of resistance. Now, there are some numerical methods, but fortunately, at least for my purposes, this value C here is 0 for greater than 0 degrees Celsius. So what I can do effectively is ignore this term here in order to calculate in order to calculate temperature as a function of resistance. Now we've got a quadratic, and it's easy to get y on the other side of a quadratic. So let's just go into that code. Bear with me, I've just got to get there. So here's the code here. So basically, it reads the device, does some conversions here, but you can see all this code here is basically you've got a quadratic with y on one side, x on the other, and you want to put x as the independent variable. So basically, that's what this code does here. Now, if you have a look here, there's a comment ugh here. This is if you're below 0 degrees Celsius, because now you have to do and what I assume from this is using some numerical methods to solve that quartic equation. So anyway, that's what the two parts here are. If temperature's greater than 0, then you're solving a quadratic. If temperature is less than 0, then you're kind of delving into some numerical methods to solve for temperature. While we're here in the code, I did have a question on a separate video. One of the things that is a bit confusing here is this looks like the Adafruit libraries, and it is indeed it is. And the question from the viewer was, can you just use the Adafruit libraries for Arduino as is without changing for an ESP-IDF application? And the answer is no, you can't. But what you can do is use those the Arduino libraries as a great starting point. So obviously, they're typically written in C++. The big difference with the Arduino libraries is, of course, all the peripheral treatment. So the way you talk GPIO, you talk I2C, you talk SPI is obviously completely different between the ESP-IDF and the Arduino. So if you see a piece of code like this, I haven't taken the Adafruit libraries just as is and compiled them into the IDF application. I've actually had to make some changes. And I'll include links to both the version that I have here as well as the version that Adafruit supplies, and you'll see that these read, bear with me while I scroll down, these read register, this code here is completely different in the Arduino version. So anyway, I hope you enjoyed this little quick diversion into temperature sensing with the ESP32. As I said, I definitely want to get back to that amplifier and do some more mods on that. So hopefully that'll be coming up pretty soon. And I hope you enjoyed this video. That's all for now.